Hi. Uh, in the previous lecture, we had discussed about dummy variable models, particularly the models in which qualitative independent variables, those variables appear on the right hand side of the econometric model. So, in an econometric model, if we are trying to explain a dependent variable which is in ratio scale, that is a quantitative variable, as a mix of quantitative variables and qualitative experimental variable. So their use of dummy variable is very helpful for us. Say we discussed how we can explain the behavior of bank credit by using various quantitative variables like deposit, economic activity, interest on lending, the degree of development of the capital market. Along with that, we can have some qualitative variables like the bank categories. We can have the differential impact of public sector banks vis-a-vis foreign banks and Indian private banks on basically the impact of all these differences in terms of ownership on bank credit behavior that we can analyze using dummy variable. So these variables like ownership category or the economic status of the state where this bank is operating, like a rich state or a poor state, these qualitative aspects we can capture using dummy variable. So like using binary of 1 and 0, say rich state, we can use dummy variable 1 representing rich state, dummy variable d is equal to 0 for the poor state, and we can capture the differential impact if at all, if it is there. Now, in addition to those simple cases which we discussed, dummy variable has very critical application in econometrics. So basically 3 applications we'll be discussing today. One is for seasonality aspect of a particular variable to check whether there is seasonality or not, and if there is seasonality, how to capture that, the degree of seasonality or the aspect of seasonality in a time series that we can analyze using dummy variable. Then structural change. Say there are certain economic relations which may change from time to time. So I'll give an example. If you are trying to assess the impact of exchange rate on exports or imports or on imports. So if you think of the pre-reform period in India, so during that period the exchange rate was managed. So it is basically regulated by the Reserve Bank of India, and it was fixed by the Reserve Bank of India. So you will not expect the market mechanism working, which will be conducive for the exchange rate impacting exports. So if you are estimating a export demand function in pre-reform period in India, perhaps if you are using exchange rate as explanatory variable, perhaps it may not be statistically significant. The coefficient of exchange rate may not be statistically significant in your econometric model. But the same relation, if you are estimating during the post-reform period, the foreign exchange rate in India became market determined. So in this regime, perhaps your exchange rate on the export demand equation or import equation may be statistically significant. So here there is a structural change. A particular variable which was not significant during the pre-reform may become significant in the post-reform. So because of this type of regime change or various several aspects, we may find the relationship between economic variables changing from one period to another. So, okay, this basically what we call in econometrics is a structural change in the relationship. So dummy variables analysis will be useful for testing various types of structural change which we can think of. A structural change in the intercept term or structural change in the slope coefficient that we will able to capture, analyze using dummy variable. Now the third very important use of dummy variable analysis is running a piecewise linear regression. There are certain relations, most of the relations which we discussed in econometrics course until now used to be a linear equation. Say, if you are running the regression of say quantity demand on price, then it is a negative relation, so you have a downward sloping curve, and that relation is assumed to be constant. Basically, that coefficient is assumed to be constant. So if slope is say 0 minus 0.2, that continues to be minus 0.2. But some relations, there are some examples in economics where we expect this relation changing, particularly when the relation is non-linear. Okay, so one particular example is estimation of threshold inflation equation. So basically, it is assumed, particularly Nobel laureate Fisher, then economist Sorel, and many studies in India also found that there is a non-linearity in the relationship between economic growth and inflation. Say, for example, when inflation is relatively low, maybe there is a positive or neutral relation between inflation and economic growth, meaning economic growth may not be influenced by inflation, but when inflation becomes high, then it becomes inimical to growth. So there is a negative impact of high inflation on economic growth. So this relation, if you want to analyze, then we may think of that up to a certain level of inflation, either the line is parallel or it is positively sloped. Then beyond a level of inflation, which what we call threshold inflation, beyond that the relationship becomes negative. So the slope of the curve itself changes. Okay, this is a piecewise example of piecewise linear regression. So this type of complicated thing which reflects reality can be analyzed using dummy variable analysis. Okay, so these three applications we will take up one after another. Let us first discuss about the seasonality. So as you know, certain time series variables whose frequency is more than annual, like if you are dealing with quarterly data or monthly data, you will see that these time series variables exhibit a seasonal pattern. You take Indian GDP data. If you plot it, you will find some repetition of the the high peak and the low points. So this may be quarter 1, this may be quarter 2, this may be quarter 3, this may be quarter 4. Then this is quarter 1, quarter 2, quarter 3, quarter 4 of the next year. Like that it continues. So if you see the quarter 1 figures for different years are generally low, quarter 3 figures of different years are generally high. Okay, so this basically what we call seasonality in the data. So if you take agricultural GDP, you'll find the Rabi season and the Kharif season. During that period, the agriculture production will it will pick up, so it will be high, and for other months and other quarters, the figures will be low. Similarly, if you take the example of sale of umbrella will be perhaps high during monsoon. It may be little high during summer, and maybe in winter the sale of umbrella will come down. Similarly, you can think of sale of ice cream. Ice cream, maybe in summer season the sale will rapidly increase, and during winter season the sale may come down. So there are various time series where, as I said, the frequency is quarterly, monthly. We may expect seasonality pattern in the data. Now, in an econometric model, if you are using time series variables without adjusting for seasonality, that is without removing the the seasonality aspect, then the econometric analysis may be erroneous. Okay, particularly those models where we are not taking care of seasonality and removing it, the projections may be incorrect. Okay, so so that's why it is important for an econometric analysis. If data is of more than 1 year frequency, when I'm telling more than 1 year, I mean quarterly, monthly, weekly, etc. So in those data series, better to check for seasonality, whether seasonality pattern is present or not. If seasonality is there, to remove seasonality, making basically what we call deseasonalization. So after deseasonalizing the data, it should be used in regression analysis. So dummy variable analysis will help us in basically detecting seasonality in the data. So this graph which I showed you, okay, if say this data is for agricultural GDP, which I'm writing AGGDP. So if you have agricultural GDP, we can analyze whether we can test whether seasonality is there or not using this type of model, where my model is A0 plus A1 D1 plus A2 D2 plus A3 D3 plus UT. Okay, here this is the quarterly data for agricultural GDP. A0 is the intercept, and D1 is a dummy variable, which is which value it takes value 1 for second quarter, and it takes value 0 otherwise. So this way I'm defining the dummy variable. D1 is equal to 1 for quarter 2, 0 otherwise. Similarly, D2 is 1 for quarter 3, 0 otherwise. D3 is 1 for quarter 4, 0 otherwise. So if you remember, we had discussed in the morning about the dummy variable trap. So where the number of dummy variables should be n minus 1 when you have n category variables. So here there are 4 quarters in a year, so our n is 4. So the number of dummy variables which we should use in the model is n minus 1, that is 4 minus 1, 3. So I have used 3 dummy variables here. So then if my estimation result is given as here, say maybe I'm finding it as AGP, agricultural GDP, is equal to 500 plus 120 D1 plus 310 D2 plus 150 D3. So if the coefficients corresponding to my dummy variables are statistically significant, then how to interpret? I can interpret that here the benchmark category is that quarter for which we are not using dummy variable. That is the benchmark category or reference category is here season 1. Okay, quarter 1. So quarter 1 value of agricultural GDP should be on an average 500, and this is for quarter 2. D1 is for quarter 2, so this should be on an average 120 plus 500, and this is dummy variable for quarter 3. Its value is 310. If it is statistically significant, then on an average quarter 3 agricultural GDP should be 500 plus 310. Similarly, you can interpret for the the quarter 4. So this way, if the t-test for the respective coefficients of the DA dummy variable is statistically significant, t-test suggests that that particular coefficient is statistically significant, then we can basically interpret that there is a seasonality pattern for that particular quarter. Okay, so assume hypothetically, if in this example we find that quarter 2 coefficient, the coefficient corresponding to quarter 2, that is D1, is statistically significant, and other 2 coefficients corresponding to third quarter and fourth quarter are statistically not significant, then our interpretation will be only for quarter 1 there is a seasonality pattern. For quarter 2, only for quarter 2 there is a seasonality pattern, and for quarter 3 and quarter 4 there is no seasonality. Okay. Now after detecting seasonality, we can basically use the corresponding adjustment to basically deseasonalize the data. Okay. So that's how this is the first important use of dummy variable, where we can use dummy variable analysis to check for seasonality, and after calculating that seasonal index appropriately, we can adjust the data before use for regression analysis. Then second application which I will discuss is for structural changes. As I indicated a little earlier, many times certain economic relations are subject to structural change, like I was giving the example of post-reform vis-a-vis the pre-reform period, where one can expect in the export demand equation, maybe the coefficient of foreign exchange rate is statistically not significant during the pre-reform period, becomes statistically significant during post-reform period, or even if it is statistically significant in both the periods, maybe in the first period, that is in the pre-reform period, the numerical value will be low, and in the post-reform period the numerical value will be high. So basically, if I take say US dollar, rupee US dollar exchange rate, So higher exchange rate implies depreciation. So it is helpful for export sale, right? So in that equation, maybe in the pre-reform period, perhaps the value corresponding to exchange rate, the coefficient corresponding to exchange rate may be 0.2, and during the post-reform period, maybe that coefficient is say 0.6, right? So even if both may be statistically significant, but in terms of numerical value, there may be change during the pre-reform period compared to during the post-reform period. So that will say that there is a structural change. Okay, there is a test known as Chow test, which is popularly used for checking structural change, and this is seasonality, basically use of dummy variable, not seasonality, use of dummy variable for checking structural change is very handy and very simple to use. So I can run a same regression, one single equation where we can check whether there is a structural change in the intercept, or there is a structural change in the slope coefficient, or there is a structural change in both. Okay, so for that maybe I can run a equation like this, where yt is my independent variable and maybe xt is my explanatory variable. So the model may look like a1 plus a2d plus a3x and plus a4 dx. Okay, here it is appearing as interactive term, and stochastic disturbance term ut appearing at the last. So here, if a2 is statistically significant, then what this imply, and d, how to define d? D is basically 1 for all the years during the post-reform period. So in India, the post-reform period say starts from 90 to 93. Okay, so for all the years after 90 to 93, okay, the dummy variable value, d value, can be 1, and it can be 0 for all the years during the pre-reform period. Okay, and if I define d that way, so then this model will be helpful for me to test whether there is a structural change in the intercept or there is a structural change in the slope coefficient. So in case a2 is found to be statistically significant, then it suggests that there is a structural change in the intercept. So when d is equal to 0, that is during the pre-reform period, this is 0, so then intercept is a1. And if a2 is statistically significant for post-reform period where d is equal to 1, then this term will be a2, so the intercept will be a1, a2. That is for the post-reform period when d is equal to 1. Similarly, we can interpret here when d is equal to 0, that is in the pre-reform period, this entire term will be 0, so then slope coefficient will be a3. And that is for the pre-reform period, the slope coefficient will be a3. For the post-reform period, when d is equal to 1, then this entire term becomes a4 into xt. So a4 into xt, here a3 into xt. So if I combine, then slope coefficient for the post-reform period becomes a3 plus a4. Okay, so this way, depending on the statistical significance of a2 term and statistical significance of a4 term, we can determine whether there is a structural change, and if there is a structural change, whether that structural change is reflected in the intercept, or it is reflected in the slope coefficient, or it is reflected in both intercept and slope coefficient. Okay, so accordingly we can have basically 4 possibilities. I can have possibility 1, which is given in this graph, where this the green line is for pre-reform period and this violet color line is for the post-reform period. So there is a difference in intercept here. Okay, so this reflects that there is a structural change, and this structural change happened in the intercept. And this is another possibility. This one we call parallel regression. The second one is a case where there is no structural change in intercept remains same, but the slope is different. This is for the pre-reform period slope, this is for the post-reform period slope. So this type of regression is known as concurrent regression. Okay, if this type of structural change is there. Then you have the third example where both the slope coefficient and the intercept coefficient is different. So there are 2 different regression lines for the pre-reform period and post-reform period. So that is known as dissimilar regression. Okay, and when there is no structural change, basically when the coefficient A2 as well as coefficient A4 both are statistical non-significant, then you may have this line where the intercept is same as well as the slope coefficient is same. We call this as coincident regression. So this way, by using a simple regression like this, we can check whether, by running simple OLS, we can check whether there is a structural change in the regression, basically in the slope coefficient or the intercept coefficient. Then the third application, which is very popular and useful, is to estimate a piecewise linear regression. So here I'm trying to show the example as I was explaining. If you can basically do on your own, you collect data on Indian inflation, maybe based on WPI, because that is the data set available for a longer period. On WPI, you basically take all those years for which inflation is 0 to 3%, and for those years you calculate the GDP growth and plot here. Okay, so this may be reflecting the economic growth for all those years on an average for which inflation is between 0 to 3. Here, for all those years for which inflation is between 3 to 6, one can calculate the growth rate and it will be higher. Then take all those years for which inflation is between 6 to 9, and for those years you calculate the economic growth, take their average, that can be given by this column. Similarly, as you go to higher and higher inflation, you will observe that the average economic growth is declining. Okay, this phenomenon is basically explaining the non-linearity in the relationship between economic growth and inflation, which I was discussing at the beginning. So for low level of inflation, in this example, when inflation is becoming higher, the economic growth is becoming higher. But beyond a point, when there is an increase in inflation, you will find that there is fall in economic growth. Okay, so it shows that high inflation is inimical to economic growth. Now, this phenomenon, if you want to estimate, basically you want to see what is that particular inflation level from which the negative relation start. Okay, that level of inflation is known as the threshold inflation. That is the inflection point at which the relationship changes from positive to negative or neutral to negative. Okay, so if you want to calculate that threshold inflation, we can use a special type of equation, which is regression, which is known as piecewise linear regression. That piecewise linear regression I can specify this way. Of course, there can be many variables which is influencing economic growth, but for simplicity I am using only one variable. Okay, and for reality, for actual assessment, we can have other explanatory variables, and to that we can augment the equation with inflation and x star etc. I'll explain. So yt may be economic growth in the year t, xt may be inflation in the year t, and x star may be that level of inflation, threshold inflation, at which the relation changes from positive to negative. Ut is stochastic error, and there are corresponding coefficients A0, A1, A2. What is important is D here. This is the dummy variable. So this dummy variable is basically constructed in a special way, little different than what we have discussed until now. So this variable takes the value of 1. The dummy variable takes the value of 1 when xt is greater than x star. For all those inflation level which is higher than x star, D is 1, and for all those inflation level for which x star is higher than xt, okay, for them D variable is 0. To repeat, for all those xt where xt is lower than x star, okay, lower than or equal to x star, the D value is 0. For all those xt where x2 is greater than x star, their D value is 1, and x star is that level of inflation which we call threshold inflation, or the inflection point at which the relation changes from positive to negative. A theoretical relation can be depicted in this graph, where this is economic growth, this is inflation. So this is changing from positive to negative at the level of pi star. That x star is pi star here, and that xt is pi t here. Okay, so for that, after specifying this regression, as I told you, by defining D this way, after running the regression, if we found that A2 is statistically significant. If A2 is statistically significant, what it suggests, for all those value of x which is lower than xt, this will be 0. Sorry, d will be 0 for them. So because d is 0, this entire thing is 0. So this entire term A2 xt minus xt star whole multiplied by d, this becomes 0. Okay, so then the slope coefficient is A1. For all those years for which xt is greater than x star, there d is equal to 1. Okay, so because this is d is equal to 1, so there the coefficient of inflation becomes basically A2. So you have a regression here where the line of this slope is A1, line of this slope is A1 plus A2. Okay, so in this example, this A2 is negative and it should be higher than A1 in the absolute value, so that this becoming negative. So this is the third important application of dummy variable, which we which are discussed importantly in application of dummy variables. So with this I'm closing the dummy variable analysis, where the right hand side variable or explanatory variable is a qualitative variable. So then we'll take off another important class of dummy variable analysis where the qualitative variable appears on the left hand side. So there are basically 4 varieties of models which we'll discuss. We'll discuss about LPM, linear probability model. Then we'll discuss about probit model and logit model, and finally Tobit model. Very interesting, and you may go through the reference for this again, Damodar Gujarati. And if you have any doubt, get back to me and wait for the next video on qualitative dependent variable. Okay, thank you.